For question number 1, we have a complex number question where they give us two complex number Z and W. For both A and B, they want us to prove different concepts using these two terms. Let's start with part A. For part A, they want us to prove modulus connection. Okay, so let's start with the left-hand side. For the left-hand side, we have modulus of Z over W. That means we have to do the division first, then we will modulus. Okay, so what is Z? Z is 2 minus 2 root 3i over negative 1 plus root 3i. But notice that, okay, in our denominator placement, we have a complex number. So, we have to remember to always rationalize our complex number when it is in a fraction form. So, how can we do this? We can multiply both our denominator and numerator with our denominator's conjugate. In this case, we will multiply both our denominator and numerator with negative 1 minus root 3i. Negative 1 minus root 3i. Now what we're going to do is we will expand both our denominator and numerator. Let's begin with our numerator. We will get negative 2 minus 2 root 3i. And then we will get plus 2 root 3i plus 2 multiplied by 3 multiplied by I squared. So that is our numerator. Whereas for our denominator, we have factored form of difference of 2 squares. So that means it will be negative 1 square minus, okay, root 3i square. Okay. So let's simplify both our denominator and numerator. Notice that these two will eliminate each other. So what we will get is negative 2 plus 6 multiplied by negative 1. Negative 1 comes from I square. And here would be 1 minus 3 multiplied by negative 1. Okay, oh, we have to remember, we still have modulus. We haven't done our modulus yet. Okay, so here we will get negative 8 over 4, which is equal to modulus negative 2. What is the definition for modulus in complex number? Let's say we have a complex number y is equal to a plus bi. Therefore, modulus of y is equal to square root of a square plus b square. But in this case, we only have a. We don't have the complex element or complex component. So here is square root negative 2 squared, which is equal to 2. With that, we are done with our left hand side. We will now move on to our right hand side. Okay, so right hand side, what we will do is the opposite. We will modulus each one first and then we will divide. Okay, so modulus of z over modulus of w. So what is our z? Our z is modulus of 2 minus 2 root 3i over modulus of negative 1 plus root 3i. Let's use the formula for modulus. Okay, for our numerator, we will get square root 2 square plus negative 2 root 3 square. Okay, over square root negative 1 square plus root 3 square. So what we can do is we can use our calculator now. So square root 2 square plus open bracket negative 2 root 3, okay, close bracket square. That would be 4 over square root negative 1 square plus root 3 square. So that would be 2. So 4 over 2 is also 2. Notice that both our left hand side and right hand side has the same value. So we already proven this. Left hand side is equal to right hand side is equal to 2. So proven. Done. Let's move on to part B. For part B, they ask us to find argument. So argument of y, so let's say we have this y here, is equal to inverse tangent B over A. Okay, so let's write down our three components. So what they want us to find, argument ZW is equal to argument Z plus argument W. So let's write down all the three different points. So 2 minus 2 root 3i, that's the first point. The second point is W. W is negative 1 plus root 3i. Whereas the third point would be ZW. So let's find this. We have to multiply Z with W. So 2 minus 2 root 3i multiply with negative 1 plus root 3i would be negative 2 plus 2 root 3i. And then we have plus 2 root 3i minus 2 multiplied by 3 multiplied by I squared. So for our constant or the real component, we have negative 2. Here would be minus 2 multiplied by 3 multiplied by negative 1. That would be positive 6. Whereas for our imaginary component, we have this 2, which is when we plus would be 4 root 3i. Let's simplify this. This would be 4 plus 4 root 3i. We must first draw our Argand diagram. Why? Because we want to know where is it. Okay, our points located. So we don't really care about like the number. Is to know where is it, which quadrant it belongs to. So real and imaginary. Let's start with Z. Okay, Z we have our x is positive, y is negative, therefore is over here. So this is Z. Z located at quadrant number 4. Moving on, W, our x is negative, our y is positive. So negative x, positive y, so it would be here, quadrant number 2. Moving on to the next point, we have positive x, positive y, so it would be over here, ZW. So ZW belongs to quadrant number 1. In order to find the argument, what we can do is we can compute this separately. Let's start with argument of Z. Argument of Z would be, okay, quadrant Z located at quadrant number 4. Remember quadrant number 4, it would be 2 pi minus inverse tangent. Okay, so what's the value? B over A. Okay, so 2 root 3 over 2. We will ignore the negative because we already used the position. So this would be 2 pi minus, okay, my calculator is already in radian mode. So shift tangent, okay, 2 root 3 over 2. So this is equal to pi over 3. So 2 pi minus answer. That would be 5 over 3 pi. Moving on to finding the next argument. Argument of W. Argument of W located in the second quadrant. So it would be pi minus inverse tangent B over A. Okay, so what is our B? Our B is root 3 over 1. So we will get pi minus pi over 3. So the answer would be 2 over 3 pi. Because this belongs in quadrant number 2. Let's now find the argument for ZW. So argument for ZW. Argument for ZW, because it located at quadrant number 1, we can just simply do inverse tangent 4 root 3 over 4. So this is equal to inverse tangent root 3, which is 1 over 3 pi. Okay, so we already know our left hand side. So this is left hand side equal to argument ZW. Let's find out our right hand side. Right hand side is equal to argument Z plus argument W, which is 5 over 3 pi plus 2 over 3 pi, which is equal to 7 over 3 pi. Notice that this is not the same, but let's change this. Let's change 7 over 3 into a mixed number. If we change that into a mixed number, we will get 1 over 3 pi, which is equal to 2 pi plus 1 over 3 pi. We are looking at the same point, but this is the second cycle. What does it mean? It means like this, okay? Because you have 2 pi, that means it goes 1 pi here, 2 pi here, and another 1 over 3. So this is 7 over 3 pi. So 7 over 3 pi is basically the same with 1 over 3 pi. Then what we can do now is we can write the conclusion. Left hand side is equal to the right hand side, which is equal to 1 over 3 pi. Proven. That's it for question 1.